Hey physics, this is Horner again, and we're going to look at momentum concepts number 31 through 41. This is the last section of momentum concepts. For number 31, you have a table tennis ball launcher is fired compared to the impulse. Remember, that's force times time or mass times change in velocity. The impulse on the launcher is the same. They are the same. So it tells you down here on the bottom, a homing cannon is constructed to deliver impulse to a tennis ball and is accelerated forward. The cannon experiences an equal and opposite impulse which accelerates it backwards. So here for the ball has a small mass, but the launcher has a big mass. So the ball has a very large velocity and the launcher has a small velocity in the opposite direction. So if you multiply the two together, you're going to get the same impulse on either side. For number 32, the cannon recoil, the speed of the cannon recoil is small because the cannon has a lot more mass. So because this cannon is so massive compared to the ball, it's not going to move very fast nor very far backwards, and that makes the ball move very, very far out. For number 33, if I made a paper cannon where the cannonball would be a lot heavier than the cannon itself, you would probably not want to stand in just behind the cannon. You'd be like Wile E. Coyote here, and you would get run over by the paper cannon because it would fly very, very quickly back towards you. And then if you notice, the cannonball would go very, very slowly. So that's the important part. For number 34, if I have a piece of putty, 2 units of momentum sticks to a bowling ball, setting the whole thing in motion, how much momentum does the system have? And it's only 2 units because it's the conservation of momentum. So it wouldn't be any more or any less, just 2. In an inelastic collision while roller skating, Granny collides with her tiny grandson Ambrose, who's at rest. So if you ignore any friction effects, Ambrose's speed after the collision will be greatest when he and Granny make a bouncing collision. So if we're thinking about this one, if I want Ambrose to be going very fast, we want them to collide and have him bounce. So if he bounces, he's going to go really quickly in this direction, and she's going to basically slow down a whole bunch. If they collide and they stick together in an inelastic collision, then they're going to have the same speed. So we want Ambrose's speed to be really big. So we really want to make sure that this is a bouncing or an elastic collision. For the next one, which is number 36, in elastic collisions, there's some things that happen. One of them is there's no lasting deformation, so it doesn't produce a dent. When you hit a tennis ball or if you hit a baseball, the ball before you hit it looks like this. And then while you're hitting it, it actually gets squished a whole bunch. And then that ball comes back out. And when you catch the ball and look at it, it doesn't look squished like this. Objects don't stick together, so when you hit a baseball, it doesn't become one with the bat. Objects that collide don't get warmer. So in the real world it would, but here we're in the physics world, so they don't get any warmer. And after the collisions, the objects have the same shape as they did before. So that's that whole lasting deformation thing. So when they hit, they're going to come off and they're not going to be any heat. They won't stick together and they will have the same shape as they did when they went in. For number 37, a karate expert executes a swift blow and splits, not spits, but splits a cement block with her bare hand. Several things here we need to know. The forces on both her hand and the block are the same, and that's because of Newton's third law. The times of impact on both the block and the expert's hands are the same, and the impulses on both the block and the expert's hand have the same magnitude. So you really can hurt yourself pretty badly if you don't know what you're doing when you make contact with this. Um, and so that's a really important thing. Don't try this at home, I guess is what I'm saying. For number 38, a moving freight car runs into an identical car at rest. So now we know the same mass. The cars come together. So this has got to be an inelastic collision. So it's not elastic, it is inelastic. They stick together. Compared to the velocity of the first car before the collision, the velocity of the combined cars is going to be much slower. So the original speed of the first car was 5. So here's the first car, 5 times its mass, we'll call it 1. The second car mass is 1, but its velocity is 0. So this term just crosses off. we can add the masses together and then find the final mass and find the final velocity, and it will be 5 over 2, which is 2.5. So we see that it went from here to here, so it would be 1/2 as big. For number 39, it says a table tennis ball moving forward with 5 units of momentum strikes and bounces backward off a heavy bowling ball that is initially at rest and free to move. The bowling ball is set into motion with a momentum of, and this is going to be more than 5 units. The table tennis ball has 5 units going in. So when the tennis table ball goes in, one going in the other direction, all right? And the bowling ball has 6 units going in the same direction. So now if we take -1 plus 6, that equals 5. To think about it a little bit better, the momentum of the ping pong ball on the way in is this way. And then on the way out, it's this way. So it's totally reversed. The bowling ball, on the other hand, has 0 momentum at first. So here, let's put the bowling ball. And then it goes in this direction and has 6 units of momentum going in this direction because it's got to offset the 5 going in and the -1 going out. So the change in momentum here, the change in momentum has got to be equal to the final, which is -1, minus the initial, which is 5, and that would be -6 units. So we're going to conserve momentum here. So this has got to be -6, and this one has also got to be a +6. So that one's a little bit more confusing, one that you really need to think about a little bit. Okay, and then this is the last one. This is number 40. You have a 5-kilogram chunk of putty moving at 10, and it sticks to a 7-kilogram bowling ball that's initially at rest. The bowling ball with its putty passenger will be set into motion with a momentum of, and you could look at all this math if you wanted to, but I think if you just do it conceptually, it's a lot easier. So the momentum before should be equal to the momentum after, or you could put original and final, totally up to you. So let's figure out what the momentum is before the collision. That would just be the mass times the velocity of the first object plus the mass of the second object times its velocity, which is 0. So that really just crosses off. And the momentum before would be 50 kilogram meter per second. And we said that that's equal to the momentum after, so it is exactly the same answer, which is 50 kilogram meter per second, and that would be the momentum after. And that is number 40. Let's go ahead and look at the very last one, which is number 41. Two gliders having the same mass and the speed move toward each other on an air track and stick together. After the collision, the velocity of the gliders is 0. So they have the same mass. So this would be m1 times v1. The second one is moving, and when they collide, it says they have the same mass and speed. So the second one is going to have the same mass, so we're going to call it m2 v2, and that's equal to m1 plus m2 times v final. Now let's go ahead and plug some numbers in. Let's just say that the masses are the same, so we're going to put 1 in for each one of the masses, and the speeds are the same. So let's call this one +2, and let's just call this one -2. That should be equal to the masses combined, which is 2, because it's 1 plus 1, and then our final velocity. What's interesting about this one is you're going to take 2, and you're going to add to it -2, so you're going to get 0. And if you divide 0 by 2, you're going to still get 0, so the final velocity is 0. And that's why after the collision, they just stop. And that is the end of the concept questions for momentum.